Okay, so this is my proof of concept for my image classification project. And what I've done so far is a basic neural network tutorial on the MIST character dataset, which is these images here, which is just handwritten numbers. And yeah, so this is the code so far. So let's get rid of this for now. So what I've got is a CSV file containing all the images, all the pixels in binary values. So the pixels are, I believe, the images, sorry, are 28 by 28. This might be a better picture. Yeah, 28 by 28. So that means there's 784 pixels on there. These are all their binary values. And the first column is the label, or what each image represents. So this image here is showing a number 1, and it goes for all of these going down. So the first thing we have here is just importing the modules needed for this program, and then using the pandas library here to open this CSV file, and then storing the CSV file in a NumPy array. And here we are, we just take the dimensions and then shuffle the data, which really just helps to like randomize the order and make sure that the neural network doesn't underfit or overfit to the data it's been given. And then since it's just a proof of concept, we're just going to shorten the data set to help it run faster, because I'm just going to take the first 1,000 images, because I believe it's like 40,000, something crazy down here. So we're just going to shorten that. And then this is just kind of formatting the data before we can put it into the neural network. So first things first is we are transposing the network, and then this is just extracting the labels, or the like correct outputs that we're going to use to compare the neural network's predictions against. So we're just taking the first column. Well, this is first row because we have transposed this, so it's the first column now, but post transposition, I guess it's the first row. And then here we're just splitting into testing and training. We are normalizing the data, so we're going to convert all the binary values to sort of fractions of 255, which should just reduce their size and kind of computational needs, I guess. Because when I've run this before using the actual values, it struggles doing the sort of operations on these big numbers because they can get quite big with the weights later on. Okay, so here we are kind of setting up the parameters for the neural network. So what we are doing here is, I've got a little picture here somewhere. So this is just a demonstration of what the transposing network was doing up here. This bit of code here. You basically kind of flip the rows and columns of the neural network. So with here, when we've got the labels as the first row, they sort of become the first column, if that makes sense. Okay, so this is kind of just a demonstration of a little basic neural network. So what we are here doing is making the layer 1 weights and layer 2 weights. So that's these lines here. Obviously they're not fill in, but you get the idea. So the weights help bring the inputs from the nodes before into the nodes in the next layer, and they kind of represent how important that input is to the output, pretty much. So obviously we don't know how important each pixel is at the start, so that's why they're just random. This NumPy function here, I guess, generates random numbers between 0 and 1, so we're just going to shift it back to negative 0.5 and 0.5 so that we have some negative weights in there. And then we do the same for layer 2, just generate the random weights. And these dimensions here are, so this is the number of nodes or neurons in the first layer, sorry, the first hidden layer, and the number of nodes or neurons in the output layer, which is 10, because obviously we've got digits 0 to 9 is what we're classifying, so it's 10 outputs. And then you make sure the array of the weights matches that of the inputs. So there's obviously 784 pixels, like we've said, so that's why that is, and the same for that, they match up. And then the biases, they're what you kind of add to the, well, I'll talk about that later. They're added on to the function in each node in the layer. So we're just generating them again. But since you only add on one bias for each node, the matrices are a lot smaller. You don't need them to be 784 wide. Okay, so once we've generated the random weights and biases, we just return them here from the function, and then we can move on. So here we have a activation function, the ReLU. I think it's rectified linear unit or something. And basically why we use activation functions is pretty much so you can solve more complex issues that basically cannot be solved linearly, because these add non-linearity to the program. So the ReLU is quite a basic one. If an input is less than 0, you just return 0. There's no output, you just return 0. Or if it's greater than 0, you just return the input. So it's pretty simple. And what happens here is in each node or neuron, you take the inputs, you multiply them by those weights we've just spoken about, you add the bias, and then whatever you get from that, you pass through the activation function, and then that becomes the value stored in this node. And then that would repeat for how many layers you have with the next set of weights and layers. So we've done the ReLU, that's that, and then that is the activation function from the first layer. And then for this output layer or the second layer, we're using softmax, which as you can see is here. So it's kind of bounded between 0 and 1 and the outputs. And what that does is basically creates a sort of set of probabilities as the outputs. And then we can use this to determine which output is sort of most likely, and we'll take that as the prediction. So all the outputs will add up to 1, so you get this kind of nice probability distribution. So that's the code for it here. Okay, and then next is forward propagation. As you can see here, so if we go back to the neural network, it's kind of like stepping through. You take the inputs, multiply by the weights, and you repeat this as many layers. So that's over here. So we can take in the weights, the bias, and the training data. So like we said, you multiply this dot product here. It's another name for matrix multiplication. So we're going to multiply these weights, the black lines, by the inputs, add on the bias for each layer, which is here. And then like we said, activate it using the ReLU function. And then simply we step through this layer, we step through the next layer, we do the same thing. The multiplication on the dot product, add the bias, pass it through the activation function, and then what this layer 2 activated represents in this neural network is the output. That is the network's prediction. So we're just going to return everything here. This is a function, the derivative of the ReLU. You don't need that yet. That's for the back propagation in a minute, so I'll come back to that. Okay, so the next function here is one-hot encoding. So this is what we'll do for comparing the output here in the output layer to those labels that we extracted at the start. So the output array, because there's 10 nodes in the output layer, it's going to be 10 by the number of images, if that makes sense. It's, yeah, matrix 10 wide, 784 down. But the labels we've extracted, because there's just one value for each image, it's only going to be 1 across 784 down. So these matrices aren't the same size, so you can't really compare them. So what we do is this one-hot encoding process. So you kind of take the range of values and you create an array in that, and then you set the value it represents to the index, if that makes sense. So 0, 1, 2, so there's a range of 3. So we change it to 3 wide, and then you just pop in. So this 0 is the first one, so it takes the first value, and 1's the middle, so it takes the middle, etc. So then the outputs and the labels will be of the same size, so then you can easily compare them. So over here in the code, that is just the code for that. That is how you create the one-hot code in Python. Okay, so once we've one-hot encoded the labels, we can calculate the error, which is pretty simple. So you call the one-hot label function, so now you have two matrices of the corresponding size, and then you can literally just subtract the two, because that is just a condition for matrix subtraction. They have to be of the same size, otherwise you cannot do it. So then we have an error, which is so if you go through the network, you've got the network's output and then the correct output. So we're calculating by how much is the network off, how wrong is it, pretty much. So then once you have that, you can perform backwards propagation. So you basically step backwards through the network and you adjust the parameters, those weights and biases, to better the output and kind of reduce that error. So how you do that is, stepping back the layers, is you use a bit of differentiation called the chain rule. So it looks like this pretty much. So if you take the derivative with respect to the layer 2, or dx in this case, you can kind of keep stepping backwards with respect to different variables like weights and biases and calculate the gradient or derivative with respect to each one. And that allows you to perform gradient descent and sort of improve the accuracy of the weights and make them better, I guess, for predicting a correct output. So in the code here, we are just calculating the error, calling that function above, and then we need to do a bit more transposition here to make the matrices able to be operated on. And then we are just calculating derivatives with respect to each variable. So this is the derivative with respect to the layer 2 weights and the derivative with respect to the layer 2 bias. And then once you have these, what you want to do is just keep stepping back in the network. We need to do layer 1 as well, because obviously those weights over here also affected the output, not just these ones. So then you calculate the error of layer 1, and then the derivatives of the layer 1 weights and the layer 1 bias, sorry. So then you have sort of these values that represent how off the weights should be for that current image. So then once you take these values, the derivatives, what you can then do is just simply update the weights and the bias, all the parameters. So you take the current weights, you take the current bias for each layer, and you simply subtract those gradients we calculated above. So, and that should make the weights better, pretty much. But what we have here is a learning rate, and this pretty much just dictates how fast the parameters are updated, because you need to make sure that you don't go too fast or too slow, because it's kind of a whole gradient descent thing. You can kind of skip the value you're looking for if the derivative is too high. So this just kind of makes sure you get the most optimal value for layer 1 weights and layer 2 weights, etc. Okay, so we've updated the weights, so we've gone forward, now we've gone backwards, and the accuracy should be reduced. So it's time to start testing. So this is just a function we use to get the prediction. So like we said earlier, the output array is 10 by the number of images using the softmax. We've got like a array of probabilities pretty much. So all we're doing here is just looking through that array and calculating not calculating, I guess retrieving the biggest value. So the highest probability, we're just going to take that as the network's output. And this is kind of only really for the user to see, so they can just kind of see what the predicted one is. And then again, this is just, so again, the prediction, again, the accuracy. So it's all kind of for the user based this. So we'll print the prediction above the one with the highest probability. We'll print the actual value it should be. And then here, we're just really calculating percentage of how many are right, or just as the accuracy really, how many have we got correct over how many there are. Okay, so the gradient descent function is how we're going to be calling, putting all this together, all the functions above to kind of train the network. So first, obviously, we get the parameters, the random weights, the random bias, using the function above. And then here we have a loop of epochs. So epochs are just pretty much how many cycles, how many times you run the network. So you go forward, backwards, how many of those you do. So we'll run it for as many as that is specified below. And then pretty much you just do what we said above. You step through forward, you calculate the outputs for the layers and the hidden layer and the output layer. And like we said, you go backwards, you backward propagate, you calculate the derivatives, you calculate how much you need to change each variable by, and then you update them. And then you just repeat that, and then over time the weights and biases should get to their kind of optimal values, the ones that give you the least error and the highest accuracy. I think this is just for the user to see here what's going on. We are printing the accuracy every 10th. I mean, you could do it, this really doesn't matter every 10th, you could do it any value, but printing the accuracy every epoch is a bit of a waste of time, so we've just gone for every 10th. So you let them know what epoch you're on, you get the prediction, call it above, you get the accuracy, you call it above. And then finally, if you return the optimal weights and biases, you can then make predictions using the network without having to train it again. So you can just call it using those settings, and it's already set up for the most accurate output with the least error. So once we have these variables here, we've got our make predictions function where so you pass in your data again because the weights are should be fairly correct and the bias, so you don't need to back propagate or update any weights. You just need to go forward. There's no need to adjust them, so we only call the forward propagation function. And then likewise, because we only going forward, the rest of the values from that function don't matter anymore. We only need the output from the output layer, which is also called here layer 2 activated. So then we get that, we get the prediction, the one that is the highest probability, and then we can return that here. And then the test predictions function is what the user can use to test the weights, the bias, the whole network on a specific image. So here we have index as a parameter. So that's pretty much just going to be which one of these images going down here do they want to add. So like this is the 5th index there, this one here. So it's a 4. So they're going to test on that image 4. So like we said, we call this make predictions. We go forward. We don't need to go backward. Here I guess we're just setting the image, which image out of the array using that index. And then we call the actual output, which was 4, like we just said from here. We call the actual output, we've got our predicted output, and then we can just display these to the user, and then hopefully they should be the same. If not, the user can see how different they are. And then there's not much point showing this now, but this basically just uses the matplotlib function at the top, and it's just going to take the data and turn it back into an image. So you can display it to the user. So it might have been pretty hard to tell for the neural network. It might have been really close. They can just see how bad or how good the prediction was from the output. And then yeah, we just call it. So here we're doing 5th. So 5th index, which would be this one. We'll call it. We'll pass in those optimal weights and biases, so the network is as accurate as possible. And yeah, we'll make a prediction. So I pre-ran the code just because it does take a bit of a while to run. So we would have been here a while waiting for it. So here you can see the outputs. So obviously the first, like we said, epochs. The up here, this is the loops. So the first loop, and these are the predictions. So as you can see, like none of them are right. So the first 3 it said were 188, and we know they should be 991. And yeah, the accuracy was only 11%. So then it just keeps going through, adjusting all the way down here. You see the accuracy goes up, and then so we get to 500 epochs or iterations, and the accuracy is actually up to 85%, which is pretty good. As you can see, these outputs have changed now. So out of the 6 shown here, it's actually got 5 of them right. It's only this first one that now it's got wrong. And yeah, as you can see here, it has actually got this prediction wrong. It's called it a 3 when in fact it's a 2, but obviously 85% accuracy is still very solid. It's still getting most of these right. As you can see here, there's 6, and it's only got 1 wrong, and plus this one. But if you were to keep running this, yeah, if you were to keep running this, it would definitely get most of them right. Okay, so after I did that, I just started a little bit on what my project will be on a different data set. So this is just kind of so here I've just built a framework for what my network's going to look like. So obviously one of the problems with the tutorial I followed there was it relies on too many modules. You need the like NumPy and pandas. So I'm going to be making my own for storing arrays and stuff like that. So this is just from a file I've created. We'll just be importing the matrix operations that I've made. And then I've just set up a basic framework. So for the layers, I'm going to include an additional hidden layer, but it will just be the same main concept as before. So the forward, the backward, the updating the parameters. So there's the 4 layers. Then we'll just create an instance of each class. So just one of each layer. We'll specify the epochs and the learning rate, and then, as we said, we'll train the neural network, passing the data, the labels, the instance of each layer, and those parameters above, and then finally we'll be testing the neural network using the parameters that it has generated. Hopefully it'll be as accurate as possible. So obviously I'm going to have to be doing my own functions and stuff. So this is a matrix file I've created. So it uses normal Python lists to create matrices instead of any functions like NumPy or whatever. So there's a lot of matrices involved. So there's going to be a lot of functions used. So this is just an empty matrix. So you input the rows, like the dimensions of what you want the matrix to be, and it will return that to you just full of zeros, which is just a normal convention for that, just to put in zeros. And then here we have a random numbers one, which is pretty much the same, but instead of adding zero to each position in the matrix, you add random numbers. So this will be used for things like the weights, like we saw in the other one. And yep, so we have the addition of matrices. And like we said with before, with the one-hot encoding, when you add and subtract matrices, they have to be of the exact same dimensions. So it all gets validated in here to make sure that works. And you can also add scalars to matrices. So if you had a matrix and you just want to add, let's say, 4 to each value, you can do that. So that happens here. And then pretty much the same for subtraction and both matrices and scalar. And then you can divide matrices by divisions, which is a function I've created here, but you cannot, however, divide matrices by each other. That is just I'm not sure why, it's just a rule of matrices. You cannot divide matrices by each other. Transposing matrices, this was code that I'd already added into the project before, but this is a code I've come up with that you can use to transpose matrices. So you pass in a matrix and you get its transposition as the output. And then matrix multiplication, this is a huge part of neural networks. So we saw with combining the inputs and the weights in each layer. So again, this is some code I've written. You pass in a matrix, you pass in another one, and you get the output as a dot product pretty much. And then again, like we said before, you can do scalars, just multiply each value in there by a scalar. And finally, the one-hot encoding, which is we went through this, how you need to adjust the dimensions of the labels to suit the outputs so you can operate on them. And then so this is just kind of what I'm going to be working through the next few weeks. So this is the image data. So again, obviously, when you go back here, you can see using the pandas library, you can just use one line and you open the CSV file, but obviously I won't be doing that. So then these are kind of objectives for how I'm going to be turning the images in the folders into the data for the input neurons. So obviously I'm going to be taking it from images, converting them into data. I'm going to be storing that in an external CSV file. So that file can then just be accessed whenever needed, instead of having to convert the images into binary values, the image pixels, sorry, into binary values every time you want to run it. So this is just a function I've created that you can open a CSV file and it will extract, like it says here, the data and the labels. So it kind of sorts into two matrices for you, kind of similar to this function here does. Data equals np.array, but obviously without using the modules. So you get two arrays, which will be used for the inputs here and comparing to the outputs. And then obviously there's just some more stuff in here, like the activation functions we're going to need. Obviously, because I've got an extra hidden layer, I might need another one in the sigmoid. And once the neural network is all set up, we will then be going onto the filing system where the program will be renaming the images with their predicted class and then sorting that into like class folders depending on their image. So all the images are then sorted into organized files. And then obviously lastly, this will all be displayed on a GUI. I'm going to be using Tkinter to display this all to the user. So yeah, that's the proof of concept. We've got a neural network working. We've got 85% accuracy, which is fairly solid. And that'll be kind of a sort of blueprint for my own one, which we've started working on here. Obviously, without the use of the functions, we're using our own here. And yeah, that's pretty much it. Yeah, thank you for watching.